We're going to explore it heute a tiny bit, yeah. A huge thanks to Brian for sponsoring this video. Good morning! Welcome back to another video. Oh no, Daddy, you're doing weird stuff to us again. First the Dividoria and now the Matrix Factoria. Yeah, my sons and daughters out there, we are going to take a look at the Matrix Factoria today. And it actually does make perfect sense if you think about it for a few hours straight. Okay, so it's actually quite an interesting topic. I don't want to do too long of an intro. We are going to dive right in a second. But yeah, it's going to be a mix of number theory a tiny little bit and linear algebra. It's quite exciting. And if you want to know more about linear algebra, for example, make sure to check out Brian, our today's sponsor. They got a bunch of linear algebra and number theory content going on over the website. Absolutely amazing. Check them out. You can find the link down there in the description. Now we are going to dive right in. So we are not going to take a look at this funny sex wheat number matrix. Okay, now this is just a little bit of clickbait here. We are going to take a look later at a more generalized version, A being equal to A, B, C, D, and even this is not the generalized version that we want to cover. We can extend this to higher dimensions. So any square matrix we can extend it to under the condition that we impose some conditions on it, which I'm going to talk about later. But before we get into this beautiful subject, into this very beautiful test subject, this beautiful individual, it looks pretty thick if you ask me, we're going to take a look at an easier version at first, a diagonal matrix of the form A00D. Okay, that's what we are going to start with, and we are going to work our way upwards. And now I would like to go a step back and think back to my complex numbers but different playlist. It was a very exciting series to me where we talked about something that's called the matrix exponentials. Has a lot of applications in solving systems of differential equations, but we need this today. It's going to be important. So if you haven't watched it already, make sure to check out the whole playlist. It's a very good playlist if you ask me. So, matrix exponentials. Yes, this was a thing. We were raising the exponential function to a matrix power. Was really weird already, but it has a lot of applications here in our problems, because if you think back to the factorial, we were able to extend this to non-integer arguments and even complex arguments using the gamma function. And when I approached this problem the first time around, I was thinking, well, why not use the infinite product expansions of the gamma function, because I don't know, square matrices works out quite nicely to multiply them together, but it was a huge mess. But there is a better definition to use, namely the integral definition of the gamma function. So if we have the gamma function of a complex argument z, where z is strictly greater than 0, do not forget this, this is really important. We can interpret this as the integral from 0 to infinity, so the real part of z, okay, not forget this, of e to the negative t times t to the z minus 1 integrate with respect to t. This is going to spit out the factorial, kind of. It's going to result in z minus 1 factorial. If we want to get ourselves z factorial, for example, if we were to plug a matrix into here, but we want to get the pure factorial out, we need to make a change of index, namely we need to take a look at the gamma function of z plus 1. If we have the gamma function of z plus 1, we are going to have z plus 1 minus 1 up here, leaving us with just z, which is a bit more convenient if you ask me, and overall this is going to result in z factorial. Okay, this is as far as the prerequisites go for now. And now we are going to suppose that we can plug a matrix into here. And this does work out perfectly, very nicely, because you can extend integrals to matrices. There's not a problem with it if it converges in the operator norm. I'm going to talk about this in a second. So before we get started, we would like to impose the same conditions that we did for z onto this integral, onto our matrix that we are having here. For example, this diagonal matrix at first. So if we plug a matrix into here, it really depends, so the convergence really depends on the eigenvalues that you have of the matrix. If you've ever done function analysis, you might have already heard about operators, for example. And operators can be decomposed into eigenvalues. Okay, this is just a spectral decomposition that you are going to have, if I remember correctly. And a very important thing here is, for our original gamma function, this integral converges for the real part of z being greater than 0. Now we shifted the index, meaning it's going to converge for the real part of z being greater or equal to 0, so it converges for all of those values. And if we were to translate this into operator theory, then this integral, and especially the exponential function, is going to converge for the real part of the eigenvalues being strictly greater or equal to 0. Okay? This is when this integral is going to converge. So if we have eigenvalues of this matrix right here, this is going to converge, this integral definition, if we have the eigenvalues being greater or equal to 0. This is what we call a positive semi-definite matrix, and this is what we are going to need here. That's a bunch of stuff lying around. So just keep in mind, if we have eigenvalues of one of these matrices, they need to be greater or equal to 0. So if we have an eigenvalue which is -5, this integral does not converge anymore. Okay, just as a little bit of prerequisites. Okay, now we are going to take a look at some square matrix. And now we are going to plug this, not square matrix, it's a square matrix, but a diagonal matrix. Now we are going to plug this diagonal matrix into here and see what we are going to get. It's kind of weird, but it's going to make sense in a second if you think back to complex numbers, but different. If we were to plug into our gamma function, our m, we are going to get out on the other side, obviously, not really obviously, but by the definition of the gamma function, m factorial, matrix factorial, being thus equal to an integral from 0 to infinity of. Now let me rewrite this a tiny little bit, because we can actually make this a bit nicer. So we have e to the negative t, and t to the z power is nothing but e to the ln t times z. Okay, so overall we are going to get e to the z log of t, so natural log of t minus t. If we were to bring everything together, this is like the little brother of the gamma function. Okay, just a little bit of rewriting. And if we were to plug our m now into our z that we are having here, this is going to result in e to the m times the log of t minus t integrate with respect to t. Okay, now we are going to have a matrix exponential. One thing that I would like to add here is that we cannot simply subtract t from this whole thing, because t is simply a scalar. Meaning, if we want to get a matrix out on the other side of this equation, we need to multiply our t by the identity matrix. This is just the identity operator that you still need to impose onto your scalar that you're going to have here. Okay, thus far that's good. Now we are going to rewrite what we have up here a tiny little bit, because, well, we can multiply scalars into our matrix. This is nice, and also we can subtract matrices from one another, resulting still in another matrix. Okay, now we are going to take a look at m times log of t minus t. By our definition of m that we are having here, this is going to result in this matrix times log of t, and we can multiply pointwise the scalar into our matrix, leaving us with a times the log of t. And also don't forget your identity matrix in 2 dimensions, 0, 0, d times the log of t. And we are going to subtract from it the identity matrix times t, leaving us with t, 0, 0, t. If we were to subtract this thing from this one, we are going to get overall, since subtraction and addition is pointwise, we are going to get that this is a log of t minus t, 0, 0, d log of t minus t. Whew, that's a lot of writing. Okay, now we are going to have an exponential function raised to the whatever the hell this is power. Okay, I'm going to rewrite this a tiny little bit more. We are going to say that those entries right here, this entry and this entry, are going to be s and r, for example, respectively. S, 0, 0, r. And we are going to call this new matrix, for example, I don't know, this is m bar. Meaning overall, in the integral, we are going to get that m factorial is hence nothing but the integral from 0 to infinity of e to the m bar integrated with respect to t. Now here comes something in that I have used in the matrix exponential video already. Namely, we are going to turn our exponential function into a Taylor series. Meaning overall, if we were to make use of the fact that we can turn this into a uniquely defined Taylor series, we are going to get the series where k is greater or equal to 0 of m bar to the kth power of a k factorial integrated with respect to t. We have done this before, and it's going to turn out to be something very nice. Good thing is, our exponential function converges for each and every square matrix that you plug into here, because the radius of convergence in the operator norm is infinite, so it really doesn't matter what the eigenvalues of our matrix actually are. So that's a really cool thing. So this thing definitely converges this exponential function, and since we defined m to be positive semi-definite, this whole integral is going to converge to m factorial overall. Now what can we do with this thing right here? Okay, the good thing is about raising a diagonal matrix to the kth power is, if we have, for example, this times itself, so squared, S0, 0, R squared, this is going to result in this matrix multiplied with itself, meaning we are going to put the entries on top of each other. It's going to give us S squared, 0, 0, R squared. Meaning, if we have this matrix m bar to the kth power, it's going to result in just our entries raised to the kth power, leaving us overall with an integral from 0 to infinity of our infinite series, where k is greater or equal to 0, of 1 over k factorial times simply s to the kth power 0, 0, r to the kth power, integrated with respect to t. Okay, now we can go a bit further and say, okay, why not drag our 1 over k factorial power to each and every point inside of this matrix, because multiplication with scalars is pointwise. 1 over k factorial, 1 over k factorial. Okay, we got rid of this. Now imagine we are adding up matrices one after another, and since addition is pointwise, we are going to add the 0th term to the first term, resulting in 1 plus s to the first power and so on, up until infinity. And since the exponential function converges, what we can basically just do is bring our sum into here on each and every term that we are going to have on each and every entry, leaving us overall with the integral from 0 to infinity of the matrix of k being greater or equal to 0 of s to the kth power over k factorial, 0, 0, and now k being greater or equal to 0 of r to the kth power over k, integrated with respect to t. And now you might notice something even better. What we are having here is nothing but e to the s power, and this right here is e to the r power by the infinite series definition of our exponential function, leaving us with an integral from 0 to infinity of a matrix being e to the s power, 0, 0, e to the r power, integrate with respect to t. And now just imagine our integral is being defined as a summation, basically. It's a Riemann sum, it's a double limit basically. But the argumentation still holds. If everything converges, we can just put this summation, this integral, into each and every entry that we are having here basically. Meaning overall, if we plug the integral into here, we are going to get the matrix of the integral from 0 to infinity of e to the s power, integrate with respect to t, 0, 0, integral from 0 to infinity of e to the r power dt. And this is basically our m factorial right now. And I want you guys to remember something. What exactly was our s and what was our r? Our s was nothing but a to the log of t, a times log of t minus t. But if we were to plug a to the log of t minus t into the original definition of our gamma function, namely in here, this is just going to result in the gamma function of a plus 1, meaning this a right here is going to be plugged into here as being our argument z. Meaning it's going to result in a factorial. Same spiel here, this is going to result in d factorial overall. Meaning, what we have here, this matrix, which is nothing but m factorial, is going to turn into the matrix, which is a factorial, 0, 0, d factorial. And this is it. This is what's going to happen with a diagonal matrix. Quite interesting, right? I hope you could follow everything I did here. I jumped over a few steps because we still need to cover up some more stuff. But yeah, this is the first major result that you should keep in mind, because now we are going to go ahead and take a look at another example, namely a more generalized one. And also don't forget, this does not only hold for 2 by 2 diagonal matrices, this holds for n by n diagonal matrices. They are finite operators and it holds for them, just by the same argumentations that we did here. Now we are going to take a look at a more generalized version, namely a simple square matrix. Don't forget, it can be finitely wide and thick. Okay, it could be an n by n matrix, But we are going to impose one more condition on it, which is going to be important. There's even a stronger result, which I'm going to talk about at the very end of the video, but I'm not going to do any calculations on it. We want A to be diagonalizable, meaning what we can do is we can express A as the following matrix, namely it's the multiplication of some matrix S inverse times the diagonal matrix T times S, where the diagonal matrix T looks as follows. So we have S to the negative 1. On the diagonal, on the main diagonal, we are going to have the eigenvalues, lambda 1 and lambda 2, because it's a 2 by 2 matrix, times S. If you have an n by n matrix, you're going to have n eigenvalues on the main diagonal. This is going to be the major result later. So yeah, how could we handle something like this now? I have written out the gamma function yet again, or just the matrix factorial, and we are going to define log times t, log of t times a, as being just log of t times this product right here. Once again, multiplication with a scalar is going to be pointwise. What we can do is we can multiply the log of t into each and every entry of the diagonal matrix here, leaving us overall with, okay, if we have log of t times a, hence nothing but s to the negative 1th power. Once again, we are going to get lambda 1 times log of t, and then 0, 0, lambda 2 times log of t times s. This is what we are having right now, and now we can plug this new definition for a times log of t into here, leaving us overall. And I'm now going to just write out the series expansion for this exponential function that we're having here. If we have the series expansion of this exponential function, it's going to be s to the negative 1 times, okay, this matrix, let's call this matrix right here, I don't know, capital V, I really don't care. So capital V times s to the kth power of a k factorial, okay? Follow me? Just writing out this part right here, leaving this all alone for now. So what exactly is this right here? Well, the good thing is you do diagonalization to make, for example, exponentiation, huge exponentiation of matrices way easier for you. Let us write out what s to the negative 1th power times v times s to the kth power actually is. Okay, to the kth power. This is going to result overall in just this thing multiplied with itself k times. So s to the negative 1 times v, s to the negative 1 times v, s to the negative 1, blah blah blah, up until s to the negative 1, v, s. Okay, and there's an s in front. And you might notice something. The matrix multiplied with its inverse is going to result in the identity matrix, blah blah blah, leaving us with k times our v multiplied with itself, k times, okay, leaving us with s to the negative 1, v to the kth power times s. This simplified quite nicely. So meaning what we are going to have here in the series expansion is nothing but s to the negative 1th power times v to the kth power times s. And even better is that our matrices S and S to the inverse, or just S inverse, S to the inverse, S to the negative 1th power, S inverse is independent of K. Meaning what we can do is we can rewrite this as S to the negative 1th power times the series expansion times S. Okay, putting this in brackets. And now we are going to be left with what we have here. Okay, and this is even better because we know what this thing right here is. This is going to turn out to be just a matrix of the exponential function of those entries that we are having here overall. So meaning if we were to plug here now just this definition into here, what we are going to be left with is that a factorial is hence nothing but the integral from 0 to infinity of e to the identity matrix negative times t now times s to the negative 1th power. Now we are going to be left with the matrix which has the exponential function up here, okay, in its entries. So meaning this is going to be e to the lambda 1 times log of t. This is just the result that we had before basically. 0, 0, e to the lambda 2 log of t times s integrate with respect to t. And what we can now do is our s and s to the negative 1 are not with respect to our integration variable t. So once again, we can not only bring it to the front and the back of our infinite series, we can also bring it to the front and the back of our integral that we are having here. Meaning overall, a factorial is going to turn into s to the negative 1th power times the integral from 0 to infinity of e to the negative identity matrix t times our matrix that we are having, and then dt integration times s. Okay, and overall, what we are going to get now is we can turn this into a matrix yet again. It's going to be the diagonal matrix with e to the negative t on its main diagonal. This is just what's going to happen. We have found this out before. What we did, we haven't split it up before, but it is what's going to happen. Meaning, this right here is going to be the matrix with e to the negative t on the main diagonals. And now, if we were to multiply this diagonal matrix with this one, it's just the first, or in general the diagonal entries multiplied together, leaving us with s to the negative 1th power. Then we can also bring our integral from 0 to infinity to the inside, yet again, just like we did before. 0 to infinity of e to the negative t. And overall, those entries were nothing but e to the lambda 1 log of t dt 0, 0, and the same spiel with the other entry right here, 0 to infinity, e to the negative t, e to the lambda 2 log of t dt, and all of this times s at the end. Meaning, what we're going to have here is, this right here is exactly lambda 1 factorial, okay? By the definition of our gamma function. This right here is going to result in a factorial being equal to s inverse, and s are going to stay how it is. And we're going to have a matrix in the middle, which is going to be nothing but lambda 1 factorial, 0, 0, and lambda 2 factorial. This is why I derived the diagonal version before, because it came in handy in here. And this basically settles it. This right here is our a factorial. This is just a factorial of a matrix. Sometimes you are going to get matrices which are not diagonalizable. But do not fear, each and every square matrix allows for unique Jordan form, okay? Meaning, you can handle Jordan forms the same way as we did here, very nicely using exponential functions, as long as your matrix is positive semi-definite. This is something that needs to hold. So even if you have a matrix which is not diagonalizable, just like, let's say, I don't know, 1, 1, 0, 1, you can still turn this into a Jordan form. This thing is already in its Jordan form, okay? We have this block up here. And then you can still handle everything using the exponential function here. This is just a way stronger result, which is also going to generalize to n by n matrices. And this basically settles it. But before we actually end the video, I would like to thank once again today's sponsor Brilliant for sponsoring another episode here on this channel. Brilliant is an online learning platform and app which focuses on active learning and also problem solving. Brilliant can help you achieve your STEM goals by working through their over 60 interactive courses in maths, physics, computer sciences, and all sorts of scientific disciplines. A huge variety of linear algebra-oriented content to work around with can be found in their precious linear algebra collection, covering the fundamentals, fractal dimensions, all the way over to diagonalization and matrix exponentials, as well as Jordan forms. To get a first impression of their content, make sure to check out one of my many live streams that I have done in the past. It's definitely worth it, check it out, they were a lot of fun, and I'm going through a lot of courses there. Linear algebra, differential equation, competitive mathematics, etc. So if you want to try it out and support the channel this way, then make sure to check out the link at the top of the description. With it you can try out a big portion of Brilliant for free already, and the first 200 people to actually use the link get 20% of an annual premium subscription, which is a really great deal considering how much content they have on their website available. It's extremely nice, and if you're still looking for a gift for Christmas for your precious one or your STEM interested son or daughter, then make sure to give them a premium subscription for Brilliant. It's definitely worth it, and they are going to learn a lot. So this basically settles this video. I thank you guys for watching. If you enjoyed this video, then please subscribe, recommend, channel like. This was kind of an exhausting video for some reason. Yeah. But other than that, check out Flammable S2. We also got STEM merch. But in the next video, I wish you guys a flammable day. Ciao.